measurement of permeability, I will leave that because I think it's a section which you can just go home and read. In fact, on the previous slides, that measurement of permeability did exist, which today in a rush we're just going to go skip that and move on to a rather important section. And if given the time, we will also look at a problem. Okay. So let's look at numbers. What do we look at numbers when we say soil permeability? Let me first right click and say it's okay. It's downloadable. You can please download this file, today's class file, on your terminal. So the typical values of permeability are is a table. It's a nice table, and I always like to use this table as a reference. The horizontal axis is the soil permeability, mind you, in centimeter per second. So if I want to take it meters per second, I just add on two. Okay, thank you. I add on two more decimal places. So that's 10 to the minus 11 or so. Usually your Montmorillonite clay would be somewhere around this value. And if you compare this to concrete, which probably has voids less than 2%, you are actually close to this value, 10 to the minus 11 or 13. So that's the lowest number. So you have a range for gravel, sand, and going down to clay. What I would like to draw your attention is to the bottom two lines. The figure, which is 1 centimeter per second, is an important number to remember, which is a boundary between laminar and turbulent flow. In other words, as long as your permeability is less than 1 centimeter per second, you can use Darcy's law. Okay, so the equations which we have used in the last class is very much applicable. The second number is 10 to the minus 9. So it says that's about 10 to the minus 11 or so. That's the lower limit of soil permeability, which majority of the clay show. So that's the other one. Of course, this table shows you can determine permeability by constant head and by falling head. So lower the permeability, you need to go falling head. That's towards silts and clay. Both the methods have been shown in the previous presentation. It exists, but like I said, we will try to skip this, and if given a chance, we may come to this measurement. The smaller one, although there are now apparatus which exist to measure permeability as low as 10 to the minus 11 or so directly. For example, you use a flexible wall permeameter. Many of our research scholars over here, they use this apparatus to measure the soil permeability of homogeneous clay. But you can also infer this from indirect measurement from consolidation test, or even from a triaxial test. The first stage of triaxial or the entire consolidation stage, you can infer or derive this from a set of equations. We will, of course, for the time being skip this, but it's a good worthwhile to really know that measurements can be done either directly, as shown by over here, or indirectly using a set of equations. Let me go to next slide, please. Over here we have another value, which is, again, I would say it's a number which you can take it as a tablet. It's 10 to the minus 4 centimeter per second is the boundary between pervious and the poorly drained soil. So pervious is coarse grained, poorly drained, I would say is somewhere over here. So that's somewhere here, poorly drained and the pervious. There are expressions which exist in literature. So rather than you measure the permeability directly, there are empirical expressions. And mind you, when you use empirical, it means whoever was the researcher, the student, he or she derived this expression based on his or her data. So it's not a safe idea to blindly follow this, but it will be quite good to understand that soil permeability, or the coefficient of hydraulic conductivity, which is K, has some proportionality. Say over here we have E cube, that's void ratio to power cube divided by 1 plus void ratio. So there is some proportional to the, if I just look at these numbers, K can be said proportional to E square. That's another expression which you can, of course, open up the equation of proportionality and get another form of equation. But if you go down, we see that this permeability also depends on soil fabric. Okay, so you can have another set of expression derived at your hometown, which includes soil, the condition of soil fabric. There is also an important aspect, which is the effective stress. Permeability also depends on effective stress. For example, unfortunately over here you have just the viscosity, not the effective stress. So you could have your own set of equation. Like I said, there is your own set of derivation. Let me move to the next slide, please. This probably is there are two sets of equation on this slide, and we will not derive this, but just look at the answer, that how the equation looks like. So if you have a flow which occurs in the horizontal direction, and there are number of layers, so H1, H2, H3 is the thickness of each layer, and the flow hits all the layers together, so they are horizontal layers. And then the average permeability KH is given by this expression over here, which is K1 H1 plus K2 H2 whole thing divided by the sum of all the heights or the thicknesses. Similarly, the permeability in the vertical direction through the same stratification. So you have layers, horizontal layers, each of thickness H1, H2 and so on. I can again have KV, which is average flow, average permeability for the vertical direction, as H1 plus H2 plus H3 and so on, divided by H1 K1 plus H2 K2 plus so on. Okay. So these two expressions, for the time being, I would like you to take them as a tablet, just digest them. They are important for many numerical problems. In the next section, I will start with seepage force, and this is an important section, and I would like you to just stay awake for the next 10-15 minutes and watch as the slides move. Seepage force is well understood if you look at the three cartoon sketch which have been drawn. Please ignore the text for the time being. Don't read through the text. Concentrate on the three cartoons which have been shown, the sketches which have been shown. The first one shows a cylinder which has soil, and on top of the soil there is water. And as shown by the triangle, the water level is maintained. Okay, it's maintained water, so it's of fixed height. Whereas at the bottom you have a valve, and in the first figure the valve is shown to be closed. So horizontal line over there, it's closed. The second figure has again a very similar situation, a constant water level at the top, whereas there is an outflow, downward flow from the bottom. In other words, to maintain the level of the water at this top surface, you have an inflow. So with an overflow mechanism such that any water which exceeds this height will just spill over. So you have an inflow and outflow. Inflow has a constant water level. Similarly, the third one, you have a flow which is upward, meaning it goes down to up, and you have an overflow mechanism at the top. It passes through the soil and it overflows to maintain a constant level. These three, let's call them as no flow condition. Okay. The second one is downward flow condition, and the third one is upward flow condition. So it's upward. Obviously, we use the same terms as as the picture shows. So let me move to the next slide, because we look at the downward we look at the no flow condition first and see what this is about. In fact, if you are asked to find out what is the total stress or water pressure and the effective stress distribution in this soil where there is no flow, we have done this a few times in our example, and just let me recap what we have done. So in the first figure, we say that there is a water level at the top of the soil, okay, and if I insert standpipes, remember we said standpipes are just vertical tubes, okay, vertical tubes inserted at different depth to measure the water level. So the standpipe which is inserted at the topmost position and the bottommost position, or even in between, anywhere I insert, they all will have the same water level and the same water level as which exists in the container or the tank. So if I want to conclude this first picture, it shows that the difference in the water level between this level and the middle level and the bottom level, there is no difference. No difference would mean there is no flow. Remember in the previous class we said in order the flow to occur, you need a head difference, a total head difference, which is the difference in the water level between the 2 points. If you recall, we said Terzaghi's model. Apologize. We use Darcy's model. Darcy's model. If I go back to the paper, we had a tube. Okay, water flowed from one direction and exit. There was an exit from the other direction. In this direction, we said if we insert a standpipe, and in the exit we insert a standpipe, the difference in the water level between the 2 standpipes. So over here it's a higher level. The difference is the water table. We call it a small h, and it was the small h which caused flow. So in other words, if the small h becomes 0, there won't be any flow. There is no level difference. Here let's come back to this figure. So if I'm asked to find out what is the total stress distribution with depth of this tank, let's start from the top surface. So please ignore the remaining sketch for the time being. Just look at the first sketch, which is shown as the total stress, which is over here. Okay. At the surface, top surface, you will find that the total stress is 0. There is no overburden at the top, so you start from 0. What is the total stress at this level? It is the weight of this water, which is H1 times the unit weight of water gamma W. That's the first one. What if I have to find out the total stress at this level, shown by the broken line, and at a depth of Z? Okay, let's visualize this. It's a total overburden at this level. It means the weight of water, which is over here, H1 times gamma W, plus this weight of soil, saturated soil. Okay, it's saturated soil because the water has filled all the voids. So the weight should include the weight of solids plus the weight of water. So I take gamma saturated, it's saturated unit weight times Z. Obviously this is again another value. If I move to the bottommost level, I have total stress equals to H1, that's over there, times the unit weight of water, which gives you a value over here, H1 times unit weight of water, plus H, which is the entire thickness, times the saturated unit weight of this over here. Okay. What about the next diagram? This is a linear triangle. It's pore water pressure. Obviously, at the surface, pore water pressure is 0. At this level, it will be H1 times the unit weight of water. And if I go down, it increases triangularly to H1 plus H times the unit weight of water. Okay. Remember, this is a no flow condition. So the effective stress is obviously this value minus this value. Both the values, if you will observe, are the same. So I get effective stress at the surface of the soil to be 0. Okay. We did a problem, very similar problem, in which the water was shown to rise above the surface of the soil, wherein the effective stress is shown to be 0. Likewise, I can derive or solve the effective stress at the bottom layer, which will be H1 gamma W plus H gamma sat minus this whole thing. If you look at this carefully, H1 gamma W and H1 gamma W from the second sketch gets eroded off, cancelled off. As a result, you have H gamma sat minus H gamma W, which is over here. Okay. So let's look at this thing in rather detail about for the downward flow, which was the second tank. Okay, we are looking at the second tank wherein inflow was from the top, a constant level was maintained, and outflow was from the bottom. Okay, just to remind you, we will ask questions in between. So I request, please, if you have any question in between, just raise a hand, click raise hand, and we'll come to you soon. Make sure your mics are ready. The mic is a major issue since last class. So it's a good idea to shake the mic to ensure it works. Okay, so for the downward flow, let's look at the first this cartoon over here. Okay, like I said, this is a flow a tank in which the H1 is maintained by an overflow mechanism. So it overflows, H1 is maintained, and at the same time the water seeps out from the bottom. And remember, we made a statement that the flow will only occur when there is a head loss. So head loss is small h. This is just a background, and hydraulic gradient is defined as small h over the length of flow. Just to recap the first line. So let's look at what is the total head difference or the head loss between point A and B. So A is the topmost point wherein you had a standpipe inserted, and B is the bottom point which you have another standpipe inserted. And because the flow which occurs, there has to be head difference, the total head difference. In this cartoon over here, it's shown by small h. That is the head difference between the two. So obviously, the total head difference between A and B, which cause flow, is small h in this figure. So if I just want to extract this in very detail, if I want to write this in detail, small h is the head loss or the total head difference between the points A and B. It is the head loss between A and B. In other words, small h equals the total head at A minus the total head at B. If you look at this figure very carefully, the total head at A is maintained. It's this value. Okay, that is the pressure head is H1. Okay, and if I say my bottom one, somewhere over here is my datum. Okay, remember we said datum can be an orbit plane, horizontal plane, and in this figure conveniently taken datum to be at this level. So if this is the datum, the total head at A would be the elevation head, which is H, plus the pressure head, which is H1. So total head at A, I have written H plus H1. Okay, total head at B is rather unknown because when the water goes out, it still has some pressure. So I'm just leaving this as obvious over here, which is total head at B for the time being. This minus this should give me a small h, which is the head difference. So if I just play around with these terms, meaning total head at B, if I take it on the left hand side of this equation, and the small h, if I take it on the right hand side, it says total head at B equals h plus h1, which is total head at A, minus h. Okay, so in this case, if I have said my level over here is datum. Okay, so in other words, if this is datum, and if I want to state the expression for total head at B, okay, just look at the left hand side. Total head at B equals the elevation head at B plus the pressure head. Elevation head at B is 0 because this is datum. In other words, the pressure head at B, okay, pressure head equals H plus H1 minus H, which is over here. And if you just think about it, it is the pressure head would mean that if I insert a standpipe at B, it should rise up to this level, right? Pressure head is the level over which the water in the standpipe goes up. Okay, so the level in the water, level in the stand is this value. If it's slightly confusing at this level, okay, if you're slightly confused, not to worry. The next slide is going to confuse you even more. Okay, just to simplify this understanding, in fact this slide over here, we do it under animation, so one thing comes at a time, but unfortunately the system we have, we can only show you blank one setup. We can't, this system is unable to show animation. So I would like you to just look at one thing at a time. we are in this entire slide, we have been asked to find out what is the total stress or pressure and the effective stress in this cartoon over here, or in this tank in which there is a downward flow. So we are still on to downward flow. The expression which we have derived in the last slide, we are going to again redo it again just to understand this clearly. Okay. So I have the soil over here, downward flow, H1 is the level of water which is maintained above A. So please read this first text. Ignore what is written at the bottom of this red line. Ignore what is written at the bottom of the red line. We are just looking at total stress value at A and at B. Okay, so we have taken two sections. The first one is A over here, B is somewhere there. So at A, what is the total stress? So we're looking at sigma A, that's the total stress at A, that's the total overburden at this level. Okay, it's H1 times the weight of unit weight of water, that's H1 gamma W. What about B? B is the total weight, the weight of the overburden. So it's H1 times gamma W, that's this over there, plus H times gamma saturated. So this level over there is H1 gamma W plus H times gamma saturated. Okay, so this is straightforward. Total stress is straightforward. What about the pore water pressure? Okay, the second row. Please, now we are on to second row. Please ignore what is written in between. Just concentrate on this second row. Okay, what is the pore water pressure at A? Let's look at this cartoon again. So it's obviously at this level, what is the pore water pressure? Equals this pressure exerted by this water level, which is H1. So pore water pressure at A equals to H1 times gamma W. Okay, we said pore water pressure equals the pressure head, meaning whatever is the elevation of water in the standpipe times the unit weight of water. That should be the pore water pressure. What about B? Okay, at B, if you recall the previous slide, we have done this. Okay, is the pressure head at B. Pressure head at B equals H plus H1, this whole thing, minus this head loss, or the total head loss, which is shown over here as small h. So pore water pressure at B equals this value times the unit weight of water. Okay. In other words, it's this height of water over there, the weight of height of water over here. So it's distance times the unit weight of water. The difference between the two rows should give you the third row, which is effective stress. Effective stress equals total stress minus the pore water pressure. Okay, in the first case, it's 0. It's the same thing. So if I just quickly look at the third figure over there, the effective stress at the top is shown as 0. Let's come back to the third row again for effective stress at B. Effective stress at B is this whole lot minus this whole lot. Okay, so that's the first lot minus the second lot. If you look at this carefully, H1 gamma W is here, and if I scroll, I'll find somewhere over here H1 times gamma W again. So these two gets eroded off. I have H gamma sat minus H again gamma water, then plus H gamma water. That's over here. So I have H gamma sat minus H gamma water, which is H gamma prime. Okay, so I've just written this as buoyant unit weight, but it's H times gamma saturated minus gamma water plus H small h, which is the head loss, times the unit weight of water. Okay, now I would like to pause over here and look at this very carefully. For no flow condition, the effective stress at B stopped somewhere over here. Okay, it didn't have this component. Okay, however, if the flow is downward, it shows the head loss times unit weight of water. This component increases the effective stress at B. Okay, this is a rather a very interesting issue, because if the water flows down, the effective stress at the bottom of the soil or anywhere in between, the effective stress is bound to increase. This concept is used, for many drawdown where you want to extract water and consolidate this ground. You normally suck the water from the ground such that the water goes down. Seepage forces are in the downward direction, which causes an increase in effective stress. So this is a very a practical usage of this particular concept. Okay. Now, I would like to pause again and ask a question. If this has, if you have slightly understood these three rows, let's look at a value at a depth Z. So anywhere in between the soil, if I ask you a question, what is the pore water pressure at this level? Okay. Please look at this carefully. What will be the pore water pressure? Try to think about it. Okay. Now, if there is no flow condition, if there was no flow, pore water pressure would have been H1, apologize, this is H1 plus Z times gamma W. However, because there is a downward flow, I have H1 plus Z, which was the original case. I have a minus of small h gamma W. Now, instead of small h, I have written IZ. If you look at this carefully, IZ is in fact the same as small h. Okay. If I divide this small h by capital H, it becomes my hydraulic gradient. So because I have divided by capital H, I need to multiply by capital H as well. So I get hydraulic gradient times the capital H, which is over here. Okay. I times Z, so it's the depth I'm looking at. This was at the bottom. If I look at any level, I get H1 plus Z, that's the no flow, minus of H, this is H times gamma W. And instead of H, I have written hydraulic gradient, which is small h divided by the length over which the soil flows. That's small h over capital H times the Z, which is the depth. Okay. We'll do a problem, if not today, but we are going to do a problem next time on this matter, just to understand this carefully. Okay, but meanwhile, I would like you to spend more time on this, just to carefully look at it when there is downward flow. Now, for the students, what I normally say, downward flow, the pore water pressure always decreases. Remember, downward flow, pore water pressure will decrease. Upward flow, we're going to look at the next case, okay, for upward flow. Okay. Okay, this is to summarize. I think I've added on an extra sheet just before the upward flow. This summarizes the no flow and downward flow. No flow condition, we have said effective stress at B was H gamma W. Downward flow is this value. Let me skip this slide because I think we have done this. Let me skip this slide as well as the next slide. Okay, it summarizes the downward flow. What happens if there is upward flow? Okay, upward flow, remember downward flow we said the pore water pressure would decrease. Upward flow, we will show in the next two slides, the upward flow, the pore water pressure in fact increases, and this is what we are going to show. So just to recap again, hydraulic gradient I is defined as head loss, small h divided by capital H. Capital H is the length over which the soil flows. So what about the head loss, the total head loss or the head difference between the flow which is upward? In this case it is upward flow, and with an overflow mechanism the small capital H1 is the height of water which is maintained. Okay, so the difference in the two is the head loss. Okay, and we are going to show that this head loss is something which causes the flow. Okay, So if there is an upward flow, what is the total head at A? Okay, remember total head at A equals, if I again follow the same analogy, this elevation head at B is 0. B is taken as datum. If this is datum, go up, the elevation head at A is capital H over here. And what is the pressure head? Pressure head is H1, meaning if I insert a standpipe at A, the water in the standpipe will go up to this level. And this height of water in the standpipe is the pressure head. So if I just want to put it in words, okay, total head at A is this fellow over here. Please ignore the remaining part of this expression. So I have total head at A equals H, which is the elevation head, plus the H1, which is the pressure head. Okay, let's come back to this expression over here. I have small h, which is the head difference, equals total head at B minus total head at A. Obviously, B shall have a greater head than A. Okay, I'm taking B to be on the higher side. We'll just look at this Y. So H equals total head at B, okay, minus, which is total head at A, equals this whole thing which you have seen, H plus H1. So if we follow the same analogy as the last few slides, I have total head at B, okay, equals, this whole lot goes on the left hand side, total head at B equals H plus H1 plus H, okay. So if you say that B is at datum, so elevation head at B equals 0. So this total head at B equals pressure head plus the elevation head. Now elevation head is 0. So in other words, this whole thing equals the pressure head. Okay. So just to put it in English, pressure head at B equals H plus H1 plus the small h, which is the head loss. Now if I pause over here and look at this very carefully, pressure head is the height of water which will rise in the standpipe. So if I insert a standpipe at B, the water in the standpipe will rise up to this level. Okay, obviously the water is flowing upward, so pressure at B should be higher than the pressure at A, upward flow. But let's look at this carefully. Pressure at B, because of the upward flow, this water in the standpipe has increased by its value, which is small h. If I just rephrase this in another words, I have that the pressure head, meaning if I the pore pressure, if I measure the pore pressure at this level at B, the pore pressure would increase by a magnitude equal to small h times the unit weight of water. Okay. Just to explain this, we have the same set of figures for upward flow. Remember, we did something for downward flow in terms of total stress, pore water pressure, and the effective stress. And I would not like you to look at everything at one go. Let's look at the first row, which was total stress. Please ignore the bottom two lines for the time being. Please ignore them. And let's look at the first row, which is total stress. Total stress at A, that's over here, this line over here, red color. So total stress at A is the overburden at this level, which is the weight of water, H1 times gamma W, which is the weight of water. When I say weight, it means the pressure, but obviously it should have units of pressure, not just the weight. What about total stress at B? That's this thing over here. It means is the overburden at this level, or the weight at this level, which is H1 times the unit weight of water plus H, capital H, times the saturated unit weight of soil, which is over here. Okay. Let's look at the second one, pressure. And I would like you to really concentrate on this row. This is the most important row of this entire slide. Please concentrate carefully. What is the pore water pressure at A? Remember, we are looking at upward flow. So if I insert a standpipe at A, because of this overflow mechanism, the water in the standpipe will stop at this level. It won't go up because there is an overflow mechanism and water is held at this level. So the pour water pressure, we said, is if you insert a standpipe at any level, I measure the height of water. It is that height of water which will give me the pour water pressure. So at A, it should be this height of water, which obviously is capital H1 times the unit weight of water. Okay, let's look at B carefully. At B, if I insert a standpipe, at B it goes at this entire H level, okay, plus capital H1 plus the head loss, which is small h. Okay, so in other words, the water in the standpipe should go at capital H plus H, capital H1 plus H. So that's the terms over here, the second one, H plus H1 plus H. That is the pour water pressure at this UB. Okay, times the unit weight of water. Okay, so pour water pressure, one instant it tells me because of upward flow, the pour water pressure has increased. Okay, so for some students we say, if you want to just make, if you feel this thing is getting too bogged down and you just want to show that upward flow, the pour water pressure will increase, downward flow, the pour water pressure will decrease. Okay. For effective stress, I would have to subtract the two and use the same analogy. Okay, so effective stress at A is 0. It gets eroded off. What about effective stress at B? I get this whole lot minus this whole lot. Okay, so if I look at this whole lot, I get H1 gamma W. So somewhere over here I would get H1, that's gamma W over there. So it gets eroded off. I have H gamma saturated minus H gamma water. Okay, that should be H gamma prime. That's the buoyant unit weight. The next one is over here I have minus of H gamma W. That's over here. Okay, obviously my effective stress at B has decreased. Okay, remember, let's go back one step. We said if there is downward flow, my pour water pressure decreases. If there is upward flow, my pour water pressure increases. So if pour water pressure increases, in other words, my effective stress should decrease. Obviously, right? The difference, you're looking at the difference. Okay. Now I would like you to go home and look at this value over here. What will be the effective stress? I'm sorry, in this figure it's the pour water pressure. What is the pour water pressure at any depth Z? So Z is measured from the top of the soil surface. Okay, please this carefully. What do you think is the pour water pressure? Obviously it equals H1 over here times the unit weight of water. Okay, then over here H, which is, I'm sorry, Z times the unit weight of water, and then because it's downward flow, I'm sorry, in this figure it's upward flow. Okay, I need some water. I think I'm getting a mixing up. Let me have a sip, please. Okay, so because it's upward flow, so the pour water pressure, because of upward flow, I have a third component which is plus small h times gamma W. Okay, upward flow is small h times gamma. Okay, now this small h is the head difference between the water. If I insert a standpipe over here, it will be the head difference between the the bottommost standpipe and the standpipe which is inserted at any level. So in this case, I have small h, or obviously any value, divided by capital H times capital H. So small h over capital H is your hydraulic gradient I, and Z is the depth which you measure from the top of the surface. Okay? Z is measured from the top. If you're getting too bogged down by this particular expression, just remember that it is the, if I insert a standpipe between the entry level and at any level, the difference in the water level in the standpipe should be the difference in water level in the standpipe should be the additional component of water pressure. There are two small sections which are very much related to upward flow. Okay. Now downward flow, we gave an example that downward flow is in fact good for us. If you want to consolidate the soil, you would induce the pore water to go down. So whenever there is a drop in water table, your effective stress increases. So in other words, it induces consolidation. What happens if there is an upward flow? Upward flow condition, there are two examples of upward flow. The first example is the quicksand condition. In quicksand condition, take the case, when the water goes up, we said the effective stress decreases, and it was given by this expression over here, which is H times the buoyant unit weight gamma prime. We had a minus small h gamma W, if you recall. Small h, you may recall, we have replaced by small h divided by capital H times capital H. And small h by capital H is a hydraulic gradient I. So in other words, you have this expression over here. Effective stress at B was capital H times gamma prime minus the hydraulic gradient times capital H times gamma W. So what happens when sigma B prime is 0? Effective stress at B is 0. I have these two. The right hand side of this equation should be equal to 0. In other words, that's H gamma prime should be equal to I H gamma W, that's over here. H and H gets eroded, or I get I, which is the hydraulic gradient, equals gamma prime by gamma water. Now this hydraulic gradient I equals to gamma prime gamma water is called as the critical hydraulic gradient. Okay, there's a term called critical. Why critical? Because it occurs at a phase when effective stress becomes 0. Okay, so in the next slide we'll just look very carefully. What happens when this effective stress becomes 0 and you reach a critical hydraulic gradient? In this case, we call that, the situation is called as quicksand condition. In quicksand condition, we say the soil, because effective stress has reached 0, it cannot support any load. If you look at the section on shear strength or the strength of soil, the strength of soil depends on two components. We say the cohesion component and the effective stress component. For sands, in particular, the cohesion component is taken to be 0. So in other words, you have the strength of soil which only depends on the effective stress. And in the previous slide we said effective stress has become 0. Okay, so if effective stress has become 0, okay, say the soil or the sand has lost its strength, and if you look at such sand, it seems as if it is boiling up, but actually it's the pressure of the water which comes up to the surface and it appears as if the sand is boiling. This is called as quicksand condition. Okay, so normally it's quicksand condition is a phenomena or a state of hydraulic gradient. Okay, it's a state of hydraulic condition or the gradient. Okay, it is not the sand. There is no a particular sand which will be called quicksand, but it is only the stage which will be called as the quicksand condition. So as your hydraulic gradient I is less than the critical hydraulic gradient, okay, you will never achieve quicksand condition. Okay, this in fact is a phenomena which has been used in many movies. Okay? If you look at some of the movies wherein you see the either the heroine getting drowned in quicksand condition and hero or let's not be gender biased, maybe the hero getting drowned in sand and the heroine probably trying to pick him up or pull him out. It shows as if, you know, the quicksand is trying to suck in a person, but in fact it will never suck in. It will be like floating in a kind of water. Okay, it's similar to that. It doesn't suck you. Okay, it's just to dramatize the movie. On this slide, there's in fact, it shows what are the various critical hydraulic gradient values, typical values. So ICR is a hydraulic gradient. For dense sand, usually it's slightly more than 1. For medium sand, it's less than 1, and loose sand is definitely even less than 1. But usually for all practical purpose, we can say a hydraulic gradient, we can take it as close to around 1. If you don't have any purposeful idea of what is the original void ratio of the ground or what is the specific gravity of the soil, normally we say, okay, if the hydraulic gradient is less than 1, where 1 is assumed to be the critical hydraulic gradient, we are safe. Okay, we are safe. In this case, we have 2 examples. Okay, the first example is over here, and in fact the first example is a question to you when you go back home. Over here we have ground. Okay, it shows already excavated, so this is an excavated ground, and that's the water table over here, somewhere here, and the water table is under extreme good pressure. So if I insert a sand pipe somewhere here, the water in the sandpipe has gone up, even higher than the top level, so it's under tremendous pressure. And this is in fact the boundary of the sand layer and the clay layer. So the obvious question is it a better idea to draw the water from the ground first and then excavate, or excavate the ground first and then draw the water out? Okay, so I just put it in English over here, the cases. Don't look at the bracket because that is a hint, that is the answer. Ignore the answer, please. I would like you to go home and look at what is the better situation. Do you excavate first and then pump out water, draw out water, or first draw out water and then excavate? Okay, that's a home assignment. Do not look at the answer. The second case is a confined aquifer problem in artesian pressure condition. Okay, this is again a case where you have take an example of a sand layer which is sandwiched between 2 impermeable layers, and the water in the sand layer is under pressure. If I do a borehole or I dig a hole through the clay layer into sand layer, there is a gush of water up, very similar to this blue tube which is shown over here. This is an artesian pressure condition. Again, it's a home assignment for you to look at the upward pressure. What happens if there is an upward flow of water? Okay. The next one is soil liquefaction. This is again a case of when the effective stress becomes 0. What happens in the case when your ground starts to shake under earthquake, under any seismic activity? When the ground starts to shake, in fact we say that the shaking is so fast that the water does not have time to drain. Even if you are using sand, a very permeable soil, because the loading is done in a fraction of a second, or maybe it lasts for a few seconds, but that loading is tremendously high under a very small load, under a very small time, that induces an undrained condition. So your pore water is not able to escape. If the pore water is not able to escape, your effective stress would become 0. So you have a case when your soil has been loaded, and your soil is loaded, your pore water pressure starts to develop. It develops up to a state that the effective stress becomes 0. In this case, again, in particular for sand, your effective stress becomes 0, your strength of soil becomes 0, or we reach a state of which is called as soil liquefaction. Okay. So the next few lines are just to put it in English. Let's quickly run through them. So loose saturated sand, when it's subjected to large loads within the short duration. Okay, For example, you said the seismic activity is the earthquake loading, wherein you have large quantity of load in smaller duration. Such loose sands, in fact, they tend to, soil sand particles tend to come closer because of the shaking. When they come closer, the pore water pressure wants to squeeze out or ooze out. In other words, the pore water pressure will increase. If the pore water pressure increases, you have a state when the effective stress becomes zero. So in such a situation, your soil tends to lose all its strength and it cannot carry any load. Okay. Now, an example of this, just to wind up, was I've taken 4 snaps of Gujarat area. Okay, Gujarat is very popular these days because of the elections coming up. But this is a case where I took in these photographs from NASA website. I would like you to look at just the 2, and I've zapped in 2 figures. One before the January 26th, 2001 earthquake, and the other just immediately after the January 26, 2000 earthquake. Now, this is a home assignment. I'm going to wind up and just to look at the case of liquefaction and the upward flow. Please compare the left hand side and the right hand side figures and see whether you do find any difference. A hint is upward flow. This is a salt pan area. Okay, salt pan area because there's a lot of salt. So more water comes up, you'll find greater white patches on the right hand side. Okay, so upward flow because of liquefaction caused, because of the earthquake loading, the upward flow caused soil liquefaction and then decrease in effective stress in quite a number of parts in this state. Okay, so as in home assignment, please compare the 2 images and see what are your thoughts on it. We will do 2 problems tomorrow. I had thought of doing a problem today, but unfortunately we have almost reached towards the end. But we will do 2 or 3 problems this time. I have devised 2 problems. So think about 3 if we can squeeze in 3 problems next time. Again on soil permeability and downward flow and upward flow. Okay. So we're going to conclude in next 2 minutes. If you have any questions, I have not seen any hand till now. I'm not sure if you people are there, and I said last time, I will not get my salary if you don't ask any question. Okay, if you have any question, please click on sand or click on hand, apologize, or write down a question on chat in case you feel your mic is not working. Maybe we can view your video and your camera. If your camera is on, we'll come to you and ask question. Okay, we are with AIT Bangalore. AIT Bangalore. Good morning, AIT Bangalore teacher. Any question, or maybe I should ask a question. Come on, people, bright people. No question. Okay. I think someone.
Yeah. It is a very interesting topic. We'd just like to know about quicksand condition, more practical examples of that other than what you have shown now in the class.
Yeah, it would be very nice to look at some more practical examples, but obviously, we have 5 more slots remaining. But if you're interested to go through this quicksand example, there is a website. In fact, if you have some time, you can go through this IIT Kanpur website. They did a lot of investigation in this Gujarat, for this Gujarat project, and they have put in a lot of photographs. In fact, a lot of excellent photographs. The two of the photographs which are borrowed, in fact, have been borrowed from this website. And if you have time, please go through that website. It explains how the liquefaction has been developed in various parts of Gujarat.
Thank you, sir.
You're welcome. Okay, let's okay. Okay, thank you very much. We have the next instructor over here. Thank you.